we were discussing the input and output impedances in a amplifier which has incorporated negative feedback. And as an example, we took a voltage series feedback circuit and we calculated the input and output impedances, how they are modified by the incorporation of the negative feedback. Now, instead of driving for all the configurations, once I have taken one example at input and the other example and output, one was shunt, the other was a series connection, then I think it should not be difficult to drive other relations. Instead of devoting time in these further derivations, we will keep it reserved for other parts of the module. Now, just to give a summary of the modifications in the input and output impedances which are brought about by the negative feedback, I can give a summary of these results. So, this is the summary for all the 4 configurations. This is the feedback configuration, this is input impedance, and this is the output impedance. Input impedance and output impedance. Now, without feedback, this is input impedance is taken as Z I and the output impedance is taken as Z 0. Now, so how these Z I and Z 0 are modified in the 4 configurations? First, we take voltage series feedback, which is also called series shunt feedback, and this is the circuit for which we have derived, and we saw that the input impedance Z I with feedback is increased to 1 plus B A Z I. It increases and the output impedance falls, and this becomes equal to Z 0 with feedback is equal to Z 0, that means output impedance without feedback plus 1 by B A. I remind that this parameter 1 plus B A, this is a positive number for negative feedback, and the value may be for this factor 10, 12, 100. So, that means that input impedance just by the incorporation of the voltage series feedback, the input impedance will rise. If we take this factor as say 10, then this will be 10 times. If Z I is 1 k, it becomes 10 k, and here if the output is again 1 k, and if this factor is taken as 10, then that will reduce to 100 ohms. So, this is the modification. Now, in the current series, feedback, which is also known as series, the input impedance and output impedance both are increased by feedback. So, ZI FB is equal to 1 plus BA into ZI, and ZO FB is 1 plus BA Z0. Both are increased. In the third, voltage shunt feedback, which is also known as shunt feedback, both input and output impedances are reduced from their no feedback values, and these are ZI FB is ZI 1 plus VA, and ZO FB is equal to Z0 1 plus VA. And finally, in the last configuration, current shunt feedback, which is also known as shunt series feedback. The input impedance is reduced, and this is ZI FB equals to ZI 1 plus BA, and the output impedance increases. So, Z out FB is equal to Z0 1 plus BA. So, these are the expressions for the impedances, the modified impedances for a amplifier circuit which incorporates negative feedback. Now, depending on the requirement, sometimes the main objective of incorporating of negative feedback besides stability is to change the input and output impedances. So, of course, in all these 4 configurations, the common factors of negative feedback, common characteristics are always there. That means, you choose out of these 4 any configuration, the circuit will show stability, the circuit will reduce the distortions and so on. So, you have to choose a proper circuit depending on your impedance requirements. And another thing you should notice, which we said also in the beginning, that when the connection of the input for the feedback network is in series, then the resistance will increase, and when the connection feedback network is connected in parallel, then the effect will be the reduced impedance either at input or at output. And all these modifications are of the value 1 plus B A. A is the gain of the amplifier without feedback, and it is known as open loop gain, and B is the feedback factor or the gain of the feedback network, and this can be calculated. So, in any feedback circuit, what we want to know? We want to know what is the value of A, what is the value of B, then all parameters concerning the negative feedback we can find out. So, this was about the impedances. Now, we continue this feedback studies, and we take the effect of negative feedback on the bandwidth of the amplifier. Effect of negative feedback on the bandwidth of the amplifier. We study this thing. Yes, negative feedback enhances the bandwidth. First, let us see what is bandwidth. In general, for any amplifier, if we plot the gain versus frequency response, meaning that here this is the input signal, and suppose for this type of experiment we keep the frequency variable. Frequency is varying. We start from very low frequencies and go to high frequencies and measure the gain of the amplifier. For example, it may be simply a voltage gain. Then what is the kind of, when we plot gain versus the signal frequency, then what kind of plot we get? This is this. Here this is the gain and this is the frequency of input signal, frequency of the signal to be amplified, frequency. Now, we are seeing that this plot can be divided easily into three regions of frequency. One is, I will come to this in greater details later, but at the moment our objective is to study the impact of negative feedback on the bandwidth. So, if here the gain is taken as A, we take 70.7%, that is 0.707 of the gain, we draw a line, and this line cuts at 2 points, here and here. This is F1 and this is F2. These are two cutoff frequencies. Lower F1 is called lower cutoff frequency, and F2 is upper cutoff frequency. Now, the difference of these two frequencies, F2 minus F1, this is called bandwidth. Bandwidth of the amplifier. Depending on our application, how much this bandwidth should be, we have to design the amplifier accordingly. It may be very large, it may be small, requirement may be of not very high bandwidth and requirement may be very high bandwidth. So, accordingly that circuit has to be designed, and negative feedback enhances. This is one of the techniques. Incorporation of negative feedback enhances the bandwidth. That means, if this is the bandwidth without feedback, then with feedback, for example, this may be like that. So, here F1 also increases, F2 also increases. F1 increases means it becomes further lower. So, it falls actually, F1 falls and F2 rises. So, the bandwidth increases. Now, how does it happen? Let us briefly explain. You have seen in the feedback systems that the effect of negative feedback is to resist any change in the circuit. I repeat that the effect of negative feedback is to resist any change in the circuit performance. Now, this is the change in circuit performance. When we change the signal frequency, the gain is falling. Here also when we go on increasing the frequency, there is a region where the gain is almost constant, and this is known as a mid frequency region, and so there is a mid frequency, and then again it falls, because we are going to study this thing soon in details. So, at the moment I just talk about the bandwidth. So, remembering the fundamental that negative feedback resists the change. So, when the frequency is further lowered, the gain will change, and that gain will be resisted by the negative feedback. It will not change that fast. So, in a way, that means that if this is F1, when signal frequency is further reduced, this change of gain will be resisted by the negative feedback, and if F1 is the lower cutoff without feedback, with feedback, that means F1 with feedback is reduced, and as we have seen that all changes are of the magnitude of 1 plus B A. So, F1 is reduced by the factor 1 plus B A. So, it becomes here, for example, F1 F B. In the same way, the F2 F B, that means upper cutoff with feedback, is increased. That means it moves in this direction here, F2 F B, and this is 1 plus B A into F2. So, lower cutoff is reduced and upper cutoff is increased, and hence the bandwidth of the amplifier increases. Now, often F2 is very large in comparison to F1. F2, this upper cutoff, is very large in comparison to F1. In that case, F2, instead of as we said, the bandwidth we can write BW. This is actually F2 minus F1, but under the condition that F2 is very large in F1, bandwidth is often taken as almost equal to f2. So that the bandwidth with the feedback, negative feedback, becomes f2 fb is equal to 1 plus ba into f2. This is the change in bandwidth. If this factor is 100, then bandwidth is raised by 2 orders of magnitude just by incorporation of the negative feedback. We can this we have just on logical grounds we have come to this expression. Let us call this expression x. We can come to this expression again by another consideration. One fundamental we should remember, that the gain bandwidth product, gain into bandwidth product is a constant for any amplifier, and this comes out to be equal to, when gain, look here, when gain is unity, that means gain falls to 1, then that is known as upper cutoff frequency and ft. What is ft? ft is upper cutoff frequency at which gain falls to 1, that is unity. Gain bandwidth product is constant for any device and for the circuit which is using that device and this product is equal to ft. If gain is taken as 1 here, then this is the bandwidth. So, ft fundamentally becomes equal to bandwidth. So, upper frequency which we are taken as the bandwidth. So, upper cutoff frequency at which gain falls to unity. Now, this expression gain into bandwidth is equal to ft. Let us call this equation y. This is true for all frequencies. If gain increases, bandwidth falls and the product will still be equal to ft. And if the gain of this we can write for any frequency, we can write equation y for any frequency, and for any frequency that gain will change and hence the bandwidth will also change, making this constant. So, if A is the gain of internal amplifying basic amplifier, that means amplifier without feedback, then we can write this equation like this: A f2 equal to ft, gain bandwidth in which equal to ft, and in the same way for the feedback circuit A fb into f2 fb is equal to ft. What I am doing, you should follow me, that bandwidth we defined for any in general for the amplifier between these two cutoff frequencies f2 and f1. So, bandwidth is equal to f2 f1, but f1 in general is very small as compared to f2. So, we can drop f1, bandwidth becomes f2, and so that we have said that f2 with feedback it increases and it becomes f2 with feedback 1 plus beta a into f2. Now, this expression we can arrive at from different angle. Gain bandwidth product for any amplifier is constant. If we attempt to raise the gain, then bandwidth will fall. On the other hand, if the gain falls, the bandwidth will increase, and this product is constant. And from this equation, gain bandwidth is equal to ft. If gain is unity, then ft is equal to bandwidth. So, we can define ft. Ft is the the upper cutoff frequency, which is bandwidth, upper cutoff frequency at which gain falls to unity. Now, this equation gain bandwidth product is constant and equal to ft can be written for any frequency. So, first is A, when A is the gain of the internal amplifier, the amplifier which is not yet using the feedback, then we can write A into f2, f2 is the upper cutoff frequency of the without feedback amplifier is equal to ft, and with feedback the similar equation can be written A fb into f2. This is the bandwidth of the amplifier with feedback, and the product is equal to ft. Now, substituting here for this AFB, we remember AFB feedback is equal to A 1 plus BA. So, here we substitute this, so that it becomes A 1 plus BA into F2 FB is equal to Ft. Since Ft is equal to AF2, since Ft is equal to AF2, this equation becomes A 1 plus BA F2 FB equal to AF2, and this A is cancelled with this, and so that F2 FB becomes equal to 1 plus BA into F2. This is the same equation as we had earlier, equation X. F upper cutoff, which is bandwidth for a feedback amplifier, equals 1 plus BA into F2, same we get here from a different angle. So, always remember that negative feedback is going to enhance the bandwidth, but what is the price which we will pay for this advantage, that the gain will falls. So, if for example, if this factor is say 50, you know that if gain earlier is say 10,000, and then with feedback it will be reduced by this factor. So, with feedback A F B, this will be 10,000 divided by 50. So, this becomes only 200. This is the price, but with this the bandwidth will go up, and this bandwidth, if this factor is 50, and let us see that F 2, that is the bandwidth of the amplifier without feedback, suppose it was 10 kilohertz. With feedback the bandwidth will be F B 1 plus B A into F 2, and this factor we have taken as 50. So, 50 into 10 kilohertz. So, 500 kilohertz. Instead of 10 kilohertz, it will become 500 kilohertz. Bandwidth increases by the same amount by which the gain falls. So, these are various advantages of negative feedback which we talked, and the only thing which we sacrifice is the gain, and the sometimes 1 plus B A is called sacrifice factor. And in any feedback configuration, all quantities are always modified by the factor 1 plus B A. So, this factor for feedback analysis, for feedback design, for feedback performance, the value of 1 plus B A, this is very important. So, this was about feedbacks. Now, the last thing about feedback is feedback implementation. Feedback implementation. So far we have been drawing the block diagrams for the feedback circuit. We isolated a amplifier, we called it basic amplifier having a gain A. Then we attached to this a feedback network, and we analyzed the circuit, and we have seen what are the effects which the feedback brings. Now we talk of actual circuits. In actual circuits, what is the feedback network and how the circuits are designed. First, I take two examples from the BJT, from bipolar transistor. These two circuits we have talked earlier, and I am sure you must have noticed that I have used even there the word feedback. One is this example. This is the example of current series. Current series feedback, which is series feedback, and the circuit will look familiar to you. This is the circuit. This is RC, R1, R2, RE. You remember this circuit we talked when we talked about the biasing methods of a transistor. In an amplifier, the emitter junction has to be forward biased, collector junction has to be reverse biased, no matter in which configuration we are using the transistor, whether in common base or common emitter or common collector, but this has to be remembered that we have to bias the emitter junction always forward bias and collector junction as reverse bias. Now, so and here incorporation of this resistance R E, that is a feedback resistance here, because in the absence of this resistance we have seen that the input is in no way connected to the output and circuit is highly unstable. Any variations will be reflected immediately in change of the characteristics of the amplifier. For example, rise in temperature will give rise, will enhance the gain, which is not desired. Incorporation of this resistance, because now through this current series feedback, the voltage developed here will be proportional to the current flowing from here. So, the voltage developed becomes the part of the input. Now, the net input which is going to the transistor is not the signal which you are applying, signal plus this voltage, and this voltage will take corrective measures and it is returned in series. That is why current series feedback. That means, the voltage developed here is proportional to the output current, and this voltage goes with this Vs with proper sign, and the sign is minus here, to the net. If for any reason unwanted situation that temperature changes or you change the device, IE for example increases, then this voltage will also increase. That means, the net voltage Vs minus the voltage developed here will fall, and that will take the corrective measures and the current will not rise. Here this beta B, the feedback factor or the gain of the feedback can be shown to be approximately equal to R E by R C, where R C is the effective resistance with the collector of transistor. What we mean by effective? Actually, this is the circuit to which we will couple a load resistance with a capacitor. Then the effective resistance is actually the two are in parallel, because for AC analysis DC voltage sources have to be grounded. This is already ground, this is to be grounded, capacitors are taken as short. So, the two resistances will come in parallel. So, then this RC will be RC in parallel with load resistance RL. If it is 4K, this is 4K, it becomes 2K. The parallel combination of 4K and 4K will give you 2K. So, that is the value we have to use. So, this is the value of the feedback factor. The other familiar circuit again from the bipolar transistor is voltage shunt feedback. Voltage shunt feedback, which is also called shunt. And this circuit again you will recall RB. I am sure you will recall this circuit. This is IB. Here the feedback is through this resistance RB. So, resistance RB forms the feedback network. How this feedback helps in bringing about the stability, this we have already talked when we were talking about the biasing schemes. This was the collector feedback bias, which is often used when, and the simplicity of the circuit is very attractive. So, and of course, it brings stability. So, through this now the current, input current IB is a function of the output voltage and it is returned in parallel. That is why voltage shunt feedback. We are sampling the output voltage and that will send the current. If for any reason current IC changes, then drop across this resistance RC will increase and this will fall. It will send lesser current and that rise in current IC will be checked, will be restricted. This we have discussed. And for high values for high values of resistance RB, the factor B, feedback factor, this is equal to 1 by RB. So, suppose it is 500 kilo ohms, then let RB be 500 kilo ohms, then B will be 1 by 500 10 to power 3, which is 1000 by 5, this is 2. Now, I take two examples for feedback from operational amplifiers. Operational amplifiers we will be talking little later, that is one of the modules, and we will go in greater details about operational amplifiers. Operational amplifiers are very important in all kinds of electronics, whether it is analog electronics or digital electronics. Operational amplifiers are popularly called as op-amps, operational amplifiers. Very large role of op-amps is there in the development, in the advancement of the electronics. Now, op-amp is a very special amplifier. Why it is called operational amplifier? This we will see later, that operational amplifiers can be used for summing purposes. Two or more signals can be summed up. This can be used as a multiplier, as a sign changer, as a differential amplifier, as an integrator amplifier, and so on. There are very large applications of operational amplifiers. Details we will study later, but for the time being few more points we have to remember. The circuit symbol for operational amplifier is this. There are two inputs, one is with minus sign, other is with plus sign. This is called inverting input, and this is plus sign is known as non-inverting. this is the output. Now, all voltages are given with respect to ground. So, if we give here a AC signal, then here the polarity, if the signal is attached, is given to the inverting input, then at the output it will appear with phase reversal. That means, there will be a phase change of pi when it is highest positive, peak positive, it will be peak negative. If we apply a DC voltage plus, it will appear as minus, and if we give minus, it will appear as plus. There are two inputs, and if the signals are given at both the inputs, then difference of the two will be amplified. This is very important system, operation amplifier, and there is a, this is not shown the batteries, this makes use of a split power supply. So, plus VCC minus VEE, but as I said, they are implied that without a DC bias, the no electronic circuit works. So, but this is not shown for the sake of simplicity of the circuits. This may be 9 volts, 12 volts, 15 volts, up to 30 volts, because there is a very large number of operation amplifiers. In the market, there are more than 2000 different types of operation amplifiers to meet different requirements. So, remembering that it is a high gain. By high gain, we mean that the most commonly used op amps have a gain, voltage gain to the tune of 10 to power 5. That means 100,000, gain of 100,000. So, it is a multi-stage amplifier, it is a direct coupled amplifier, and so on. Now, the one beauty, why this is so popular, that is different, but why we are taking examples from here, that in these two circuits which we discussed, these two circuits, either this or this, here the feedback network was the part of the main circuit. Here in op amp, we externally connect the feedback resistances, and there it is easy to understand and to drive the things. So, first we take just two examples. The one is voltage series feedback. Voltage series feedback, which is also series shunt feedback. And the circuit is this. If we want to use from out of these two input terminals, if we want to use one, the other is grounded. So, that way if we ground this non-inverting terminal, then we are using as a inverting amplifier, and if we ground the inverting input, then signal will be fed to the non-inverting input, and then we are using it as a non-inverting amplifier. And if signals are given to both, none of the two is grounded, then we are talking about differential amplifier, and the difference of the two signals will be amplified. So, here this is RF R1, this is of course plus VCC minus VEE. This plus VCC gives reverse bias to the collector of the transistors, and this forward biases the emitter of the amplifier. Here this is RL, and the voltage developed across RL, the load resistance, which is V0, a fraction of this is fed back through resistance. So, this R1 and RF network forms the feedback network, and the voltage drop, this is also acting as a voltage divider. So, V0 is divided, and the one which is dropped across R1 is fed back in this circuit. That is the feedback connection, and here the voltage which are feeding is proportional to V0. This is voltage developed, here is Vf, and Vf varies in proportion to V0. And lastly, there is current shunt feedback. Current shunt feedback, and this is this. Basically, this is the here operation amplifier is acting as a current amplifier. So, this is Is, which is divided into two parts, IE and IF, and this current IF, which is the feedback current, it is varying in proportion to I0, and obviously here IE is Is minus If. So, this is the error signal which goes here in the amplifier, and B can be shown to be equal to parallel combination of R1 R2 divided by R1 plus R2. This is the expression for B. This is the feedback part, feedback circuits, feedback analysis of the amplifier, and the remaining part of this module, that is the coupling methods and study of RC networks, and why we get that kind of frequency response which was shown. We will be talking that.